second one times the first one. So derivative of x with respect to t is dx dt, remember, right? Right, what is the derivative of x with respect to t is dx dt, right? Times tangent theta plus derivative of tangent theta, secant squared theta, secant squared theta, that times d theta dt. Awesome. Okay, so where did that come from? Well, you're taking derivative of tangent of something, right? Which is secant squared of it, but then you go inside and take derivative of theta. Derivative of theta with respect to t is d theta dt times x. That's finishing off product rule. Yes?
The d theta dt came from?
We're taking the derivative of tangent of theta, right? So derivative of tangent of my hand is secant squared of my hand, right? Secant squared of my hand. Then chain rule says go inside and take derivative of what's in here. Derivative of theta with respect to t is d theta dt. Okay? Now the x comes from where? Finishing off the product rule, right? I'm almost done. What else do I need here? Equals 0. Right? Derivative of 2 is 0. Now look, if you didn't like this and you didn't like the product rule, here's what you could have done. You could have left this over here, taken the derivative, which would have been this. Then here you would have had to realize that that's really 2x to the negative 1 power. Bring the x up. And then you would have done power rule, negative 2x to the negative 2. And then derivative of x, which would have been this. This is your alternative if you didn't like me clearing the fractions. Okay? But they turn out to be the same thing. I mean, at the end of the day, they're the same. They give you the same result, I should say. Okay, let's go by and check off the things that we're good with. Dx dt, we have that, don't we? D theta dt I want, right? Do we know what x is at the moment in question? Yes, that was root 32, which we would have had to have solved for, right? All right, I think we are going to be able to do this without using a calculator at all. Because now we can go back, we can go to this picture, right? And theta's right here. What is tangent of theta? 2 over root 32. Opposite over adjacent, right? Opposite over adjacent. Okay, this right here, just so everyone's clear on this, this means secant theta squared, right? That's what that means? So what is secant theta? The reciprocal of cosine, right? Cosine is adjacent over hypotenuse, so secant is hypotenuse over adjacent. So this is 6 over 32, 6 over 30, root 32, sorry, squared. Understand? I didn't need a calculator. Now, just for the sake of doing it, if I had to use a calculator, like if for some reason I needed to know what theta was, you could get theta from this picture by doing something like this. I could write sine theta is 2/6, right? And then I could do, on my calculator, arc sine on both sides and get my calculator out and do the inverse sine function, and that would recover the angle. You would just have to remember from pre-cal that there are some domain restrictions on inverse trig functions, and you can't always trust the answer that your calculator spits out because it may be restricted. Okay, this is not pre-cal, I'm not going to get into that, but this is how you would recover that angle. All right? Fortunately, because we didn't need the angle, we needed tangent and secant of it, we could just go right off the triangle to get those. All right, I think we're there. Let's just put this all together and we'll have an answer. Okay, dx dt was negative 600. Then this was 2 over root 32. And then plus we have 6 over root 32 squared, and then times d theta dt, and then times x, which was, I forgot. Oh, root 32 equals 0. There it is. Not pretty, but it is what it is, right? So if I was going to try and solve for this right here, I would take this to the other side, and then I would start multiplying by reciprocals and things like that. I'm going to give you an exact answer, and then we'll get the decimal, all right? Because I think it's worth us working through that. How about we do this? 36 over 32 times root 32 times d theta dt equals positive 1200 over root 32. Okay, so all I did there, this right here, the 2 and the negative 600 is negative 1200 over root 32. Then I moved the whole thing to the other side, which made it positive. Right? I squared these two things. If I square this, I get 36. If I square that, the root goes away, right? And then I had a root 32 here. So I just slid it out here next to this. So do y'all see where this all comes from? Yes? Now what I'm going to do is like multiply this side by the reciprocal on both sides, and that should get my d theta dt by itself. So what would I be multiplying by over here if I wanted to get rid of this over here? 32 on top, 36 on the bottom, and root 32 on the bottom. Because really this is like a fraction like that. So I'm just flipping it. On both sides it'll go away over there. Algebra. D theta dt equals this root 32 and root 32 come together to be a 32, and then we cancel with that. So you get 1200 over 36. I know 6 goes into both of those. It's 12. 12 goes into both of those. 12 goes into the top 100 times. 12 goes into the bottom 3 times, which is 33.3 repeated. You agree? 33.3 what? What? Well, I'll agree with the per hour. I'll agree with that. Degrees per hour? Radians per hour? What is it?
Angle?
It is the angle, but is it in degrees or radians? It's in radians. Unless we measured it some other way, it's always going to be in radians. Radians per hour. Now, do y'all remember how to convert from radians to degrees? 180. Multiply by 180. So someone on their calculator, take this, multiply by 180, and divide it by pi. And what would that be? It's going to be a big number.
1907.895.
Degrees an hour. So when the plane's flying over, right, at that instant in time, right, when it's 6 miles away, the angle is changing at a rate of 1,907 degrees an hour. Now, an hour is a long time. So it's like, as it's moving, once it gets to that instant, if you were just to keep moving at that rate and forget the plane's there and just keep moving at that rate, that's the rate at which you're turning. So imagine, again, back to the anti-aircraft computer is constantly processing these numbers and trying to lead out in front. You know, they know, if I shoot now and it's that far away, I know that the bullet's going to meet the plane at some point, but I have to be turning. So it's doing all these calculations very fast, right? Okay. Some computer programmer figured all that out. They have to take a lot into account. And I guess if you spray enough lead out there, you'll hit it, right?
Doesn't always do it.
No, don't. Don't always get it. All right. So we've seen the use of some triangles, right? I don't think I'm going to do this one right now. I'm going to do this one. This is like a classic Calculus 1 related rate problem. Like most Cal 1 students will see this problem. A conical cup. This will be our last problem for the day. I think I've given you sufficient headache. A conical cup is 4 inches tall and 6 inches wide. Water is being poured into the cup at a constant rate of 2 pi cubic inches per second. How fast is the water level rising when the water is 1 inch from the top of the cup? So I'll draw my pictures in a second, but so I'll make sure we understand we have a conical cup. And I am pouring water into it at a certain rate, right? Water is being poured into the cup at a constant rate of 2 cubic inches per second. So how fast the water is going in is the same. And I showed you a picture in class last time showing that initially, in the beginning, the water level rises very quickly. But because it spreads out, right, you get more volume, it's going to slow down. As long as I pour in at a constant rate, it's going to slow down on its way up. All right, we'll draw our pictures. Did I tell you all about these refillable markers that they've, yeah?
New markers?
They're these really good markers that they're refillable.
Or you bought them?
No, they were down the office.
Nice.
And they don't have the refill stuff. So I said, what am I supposed to do with that?
That's a taxpayer dollar.
Yeah.
Stewardship right there.
All right, so here are my pictures. So I told them, I said, these are like the best markers I've ever used. They're so good. And I said, where's the refill stuff? They're like, those are refillable? All right, what I am given, what I want, and an equation. Let's try that out. All right. Let's just draw a picture of a cone being filled with beer. No, beer, water, doesn't say, right? If I change that to 40 inches and 60 inches, you'd be happy? Big old, that would be okay?
I don't want it to get hot now.
Yeah. I'm sure you could chill it somehow. All right, so here we go. I can add more to this cone in this general picture, right? It's 4 inches tall, 6 inches wide. So it's not really drawn good here, but 4 inches tall, 4 inches tall, 6 inches wide. Yeah, not drawn to scale. It's all right. Those aren't going to change, right? And as far as the dimensions of the cone, that's not changing. How about the instant in time that I'm referring to here? It's the level of the water that's in it, right? And I have blue here. So we have water inside of this. Oh, it's 1 inch from the top, so I'll move it up a little bit. Right? So it's 1 inch from the top. That's the instant in time, right? Okay. Anything else about what I'm given, what I want? I mean, anything that you can throw up here.
You have what I guess would be df over dl, which would be
Wait, D what?
dl. I used f for flow rate, so it would be 2 pi cubed.
2
Your rate of
pi.
flow, right?
It's cubic inches, right?
Yeah.
Per second. If it's cubic inches, it's a measurement of volume, right? So we'll go with dV dt because it's a change. You could use any variable you want, but I'm going to stick with volume because it is a measurement of volume. dV dt, the volume is changing at a rate of 2 pi cubic inches every second. What do I want?
You want to know how fast the water is rising at 1 inch?
How fast is the water level rising when it's 1 inch from the top? I don't have anything on any picture that shows my water level, except for the instant in time. But in my general picture, I don't show a water level. So I better go put a water level in there, right? So, and it doesn't have, it's not 1 inch from the top. It's moving, right? So that's just got some arbitrary height to it, doesn't it? And we could call that anything we want. Do you want to go with height, h, or you want to go with x? It doesn't matter. You go with y. Just can't use v because we've already used v. Or we could do w for water. It doesn't matter. Let's go with h for height, okay? So go back to this picture here. Do I actually know what h is in this picture?
3.
H is 3 in this picture, isn't it? Because it's actually the distance from here down. 1 inch from the top really means 3 inches up, right? All right, we're starting to get somewhere.
Yep.
What do we want?
We want the height times t.
Right, we want dh dt. How fast is that h changing at exactly the moment what? H is 3. See? So we want to be careful. We don't want to say h is 1, right? 1 told us the distance from the top, but we're measuring h from the bottom. I just need an equation that relates the volume to h. Whoa. Volume to h. Okay, well, we have a formula for volume, I think. Volume of a cone?
1/3 pi r squared.
Yeah, so let's do this over here. In your formula sheets, you'll have a picture that looks like this. Well, it may not look exactly like this, but they give you a radius, they give you a height, and they tell you that the volume of this is 1/3 pi r squared h. That's the formula that they give you in the book. Okay? Yes?
Yes.
All right. So I can use that here. I'm talking about the water. What is the volume of that water? The volume of that water should be 1/3 pi r squared times h. We're using h, right? Like if you used w here, then this would need to be w. Or if we used x here, this last piece would have to be x. But we used h, so that works. We have an equation that relates v and h together right here. Everything's looking okay right now, but there's a problem. Does anyone see what the problem is? If you differentiate this, aren't you going to get a dr dt out of this?
Yes.
Right, because r is a variable. Do you agree? As this water comes up, your radius is changing. It is not fixed. So when we differentiate this, we can't hold that constant. Therefore, we're going to get a dv dt, we're going to get a dh dt, which we're happy about. We're going to get a dr dt, which we are not happy about. Understand? So how do we get around this?
Couldn't we solve for the radius of the cone 3 inches tall? At that point.
Well, the cone is 3 inches radius. I agree, but that's not the water.
Yeah.
Does everyone understand the problem here? And like we've run into this issue? It would be really nice if in this problem I could somehow eliminate r. Like if r wasn't in here, like if it was h instead, right? Like somehow if I could write r in terms of h, maybe I could make that happen.
Move everything in one space.
What do y'all think? Any ideas? Got it all cleaned up over there? Okay. Have any ideas?
Maybe change it.
You know what we're trying to do?
Yes.
Okay. Let me ask you a question then to keep you engaged. Imagine I grabbed this sword, okay? And I took this cone and I sliced it right down the middle. Okay? What's your name? Sarah. Tara. Okay, Tara. So I'm just trying to keep you going here. Tara, if I slice this down the middle and took the, and let's act like the water didn't flow out, okay? The water's still there. Okay, so I'd slice it and I open it up and look at it. What do I see? What? Hold on. Tara, what would you see? Like what geometrically would you see if you sliced that cone down the middle and opened it up? Can you visualize what that would look like? I'm asking, okay, so look, if I take a sphere and I cut it down the middle and open it up, what do you see? Circle. Okay, so I'm asking you to take this picture, cut it down the middle, and tell me what you see. Tara's telling us. Everyone, what do you see? Okay, so like what?
Like a regular.
Okay, like a right triangle like this? No. Okay. So you see this, right? Okay. And you also see the water in there. You see this triangle. Right? That's what you see? Everyone see that? Okay, now, what I'm going to do next is I'm going to go to the midpoint. I'm going to drop straight down like this. All right? Y'all still with me? Thank you, Tara. I was just trying to get you kind of going here. All right. Now, I'm going to draw this. Just going to look at right side of it. I could look at the left side, but I'm just going to do the right side. All right. You want to keep going, Tara, or you want me to leave you alone?
No.
You want me to stop? Okay. I'm just messing with you because you were cleaning your phone, so I just thought that was funny. It's like, wow, my screen's dirty. All right. Help me label this triangle. There are certain things we know and certain things we don't know.
You have two right triangles on the bottom. You get a 90.
Label these. Label these. Well, yes, this is 90. That's 90. We know that.
You have a 92 at your water level.
A what?
What?
Did you say 92?
At the water level, you have a 90 degree.
Oh, 90. Okay, I thought you
And
said.
so you know out of there you're going to have 90 degrees in the other two angles, so you'll be able to label those eventually.
The height equals 3.
You know the height is
Height is what?
Height is 3 inches to the water.
What height's 3? From where to where?
From the bottom?
Water level to the ground is 3?
Yes.
Yes or no?
Yes.
Yes or no?
C.
Water level to the ground is 3?
Yes.
No. You've frozen it. You've frozen this in time. You have fixed it. You're not allowed to fix it yet. It's H, right? This to here, this is H, right? It's H. Remember, let's not lose sight of what I'm trying to do here. I would love to not have that R there, right? So some crazy way I'm coming to the geometry of the problem, taking a cross section of the picture, and seeing if I can set up some relationship between H and R. Okay? So now I have that this is H. How about this right here? That's R. That's changing, isn't it? The radius of the water is changing. That's R, but that's R in there. Now the key part of the problem, of this part. Is there anything else on those triangles you can label? How about the big triangle?
So you know it's going to be 3 inches.
How wide is this on the top?
3.
3. Is that changing?
No.
No, that's your cone.
Constant.
Okay, that's your cone. And then what about the distance all the way from here to here?
4.
4, that's not changing. This is your container, right? The vessel is not changing here. And look what I've created. Do you know what we call these? If you have a triangle that looks like this, that's 3 and 4 and a 90 with an angle here, which I'll call theta. And you have another triangle inside of it that's smaller like this, where this is R and this is H. In the same theta, you have what are called similar triangles. Similar triangles are triangles that share the same angles, that have the same angles. And there's something very important about triangles that have the same angles. all the, what's the word I'm looking for? All of the sides are proportional, not, I can't believe I forgot the word, corresponding sides. The ratio of corresponding sides are equal. The ratio of corresponding sides. So do y'all see the small triangle here? I just moved it out on its own. I can take the ratio of any corresponding sides and it will be equal to the ratio of any other two. In other words, I could take this 3, divide it by that r, and that should be equal to this 4 divided by h. The ratio of corresponding sides must be equivalent. So if you need to, you can go back and review similar triangles for this, but I can set this up. I can write 3 over r is equal to 4 over h. All right? Because they're similar triangles. I could also have done this many different ways. I could have even done 3 over 4, short side over long side is equal to r over h. And there's as long as they're corresponding, you could do r over 3 is h over 4. What you could not do is 4 over r is 3 over h. You can't do that because they're not corresponding sides. Do you all understand that? Now, why did I go through all this stuff in Bugterra about this?
The relationship of R.
I have a relationship between r and h now that's dictated by the cone. And so I can come in here, and what did I say I wanted to do? Get rid of this r? So I'm going to go ahead and I'm going to choose this one right here. I like that one. Because r is sitting there on the top, isn't it? And I'm going to multiply both sides by h. So isn't r equal to 3/4 h? Okay, come back here. Volume is 1/3 pi times 3/4 h squared times h. This is basically telling you that for this cone, your radius is always 3/4 of the height. For this particular cone, your radius is always 3/4 of the water level. And that would be for the whole time it's moving up. This will always be 3/4 of that. It makes sense? Because when you get to the top, isn't it like 3 and that's 4? Okay. All right. We are happy with this equation now because it has just h in it and v, and there's no more r, and we had to do some work for that, didn't we? All right. I'm not ready to differentiate. I'd like to clean that up a little bit. All right, cleaning up. Volume equals 1/3 pi. Now, I'm going to go ahead and square that. What happens when I square that? Get 9/16 h squared, but then times another h out here, right? So h cubed. And that means volume is 3 pi over 16h cubed. So I just, reduced this and moved those together and got my constant out front. There it is. Of course, for this cone, your volume is always 3/16 pi times the height cubed, right? Of course. We just figured out that formula. Differentiate. So when I differentiate this, well, you know what? Why don't you do it? Go ahead and differentiate that and solve for what you're supposed to solve for, and I'll take a poll here in about 3 or 4 minutes to see what answers we get. And let's get a decimal answer, all right? .395. So I've done the work up here. This is your derivative. And then just plugging all the different values in. dV/dt was given to us to be 2 pi. The height of the cone, or the height of the water level at this moment in time was 3. So I plugged everything in right here, 2 pi, and then I plugged 3 in. And then this is just cleaning up. And so, any questions on that? Now it's .395 what? So dH/dt is .395. H is measured, the height was inches per second. So it's coming up at like 0.4 of an inch per second at that exact moment. Okay, let's talk test. Does anyone have their test from last class? Or the first test? Anyone have it with them? What did I end with? Like, what was the last question on there? Yeah, let me see.
It was find the equation of the line.
Tangent, okay, so
And bonus question.
tangent, okay. So let's take a look. Of course, I'll prompt this with, make sure you've done your homework, right? Remember the first exam? That a good percentage of those problems came from the homework. I mean, almost like number for number from the homework. So I will say that, make sure you look at your homework, all right? I'm also not going to record this.